All right, our second speaker is Nicholas Kiriazis. Nicholas is a master's student in statistics at McGill University. His thesis was about statistical modeling in sports and was supervised by Professors Christian Genest at McGill and Alexander LeBlanc at University of Manitoba. Nicholas was also a player coach at the very amateur level for a decade, long before developing his interest in sports analytics.
Hello, everyone. Thank you for being here today. Hello, everyone. Thank you for being here today. So this is research I've been working on during my master's degree and was supervised by Professors Christian Genest and Alexandre Leblanc, who unfortunately aren't here today, but a huge thank you for them for making it possible. So I'm obviously not the first person interested in measuring individual rebounding ability, which is why there's quite a few existing metrics which can be more or less more or less problems. So the most popular of which is obviously like some form of scale rebounding count, like things like rebounds per game, rebounds per 100 possessions, things like that. And the problem is that they obviously don't account for how many shots were even missed in the game, which means not even how many opportunities for rebounds there were for each player to collect. So an obvious improvement is to look at something like rebounding rates or just what's the proportions of misses. So although that's great because it's accounting for how many shots were missed, we have a whole new problem where rebounding rates don't just communicate ability to be about the player, but rather compute ability to convey information about the whole lineup. So for example, if you have two really strong rebounders playing together and you use their rebounding rate to evaluate them, well, they're actually making each other look bad, right? Because they start stealing these rebounds away from each other. And both these metrics suffer from the serious drawback that they only credit the player who's actually collecting the rebound, right? But let's say we have some player who's really good at boxing everybody out and isn't necessarily grabbing the rebounds themselves. Well, we probably want to credit that player for their contributions to the team rebounding, which none of these metrics would do. So this is obviously not a new problem, and it's why Engelman suggests applying Rosenbaum's adjusted plus-minus framework to rebounding data. But again, this has a few drawbacks that I'll get to in a couple slides. So before we get into the nitty-gritty of the math, I just want to give a bird's eye view of what we're going to be doing, and it will help kind of direct the conversation we'll be having today. So the first key assumption we'll be making is that every player has this intrinsic rebounding ability that belongs to them and doesn't depend on their lineup mates. But what does depend on the lineup mates are the actual rebounding rates. And today when I say lineup, I'm going to be referring to like the 10 players on the court, not just the 5 guys per team. So with this in mind, we propose factorizing the individual rebounding rates into these two terms. So we have this first term that we call the beta level, and it's the probability of the team getting the rebound. And then we have the probability of any specific player on that team getting the rebound conditional on the fact that their team's actually collected. And the idea of factorizing it this way is that the model's, at least in theory, expressive enough to capture players who are helping their team win versus players who are just kind of snagging rebounds that their team would have collected regardless of their involvement. So before we get into defining the models, I just want to go over one technical detail. So we're going to use data from the 2020-21 NBA season to estimate the parameters. And if you can see from the histogram of playtime distribution, there's a little bit of a peak around 0. So this is guys getting called up from the G League, guys signing 10-day contracts, stuff like that. And the problem is we end up with a whole bunch of extra parameters that will lead to noisier estimates and to overfitting in the training data. So this is a known issue, and there's a few existing approaches. So what Rosenbaum does in his APM framework is that he takes all the players having played below some threshold, replaces them by a single parameter. Joe Sill in his RAP, regularized adjusted plus-minus framework, does something a little bit similar in spirit, where he has this identical prior across all the parameters. And these things might make sense if you're working with plus-minus data, but at least in rebounding, it doesn't really make sense to assume everybody's equivalent. So for example, let's say on your G League team, we have this 7-foot rim running big man, and you also happen to have this 5'10" slashing guard type. Even though we might not have enough data to detect that they're different, it seems natural to assume that they are in fact different. So we did something kind of similar to this, but instead of replacing all players by one parameter, we group players who have very similar play styles and replace each group by its own parameter. And if I were to go into too much detail, this would actually double the length of my presentation, so I'm just going to point you to my thesis. I just want to mention it because it appears on some of the plots later. So the data is all publicly available. It's all super easy to access, and it's basically just play-by-play data that we got through the NBA API. There's one technical thing I want to note, though, and that I kind of lied earlier. Not all players actually collect rebounds. So if the ball is sent out of bounds after a missed shot, the team that maintains possession is actually allocated a rebound, but no individual player is. So if you sum up all the individual rebounding rates, it's actually slightly less than 100%. And I know this seems like pedantic, whoops, but it's actually really important for how we define the models later. So just make a mental note of it. So we'll start with the gamma level rebounding model, which we call as conditional on the team having collected the rebound. And since we're conditioning on which team has it, we can think about each missed shot as a multinomial random variable with 6 outcomes, right? One for each of the 5 players on the team, and then that 6th possibility of there being a team rebound because the ball bounced out of bounds. And since we're dealing with multinomial random variables, it seems natural to use something like multinomial random regression or multinomial regression. The problem is that in our instance, as opposed to traditional multinomial regression, each one of the outcomes doesn't have, each one of the observations, doesn't have the same set of possible outcomes, right? Depending on who's on the court, the possible rebounders changes, and we wouldn't want the model to predict that the ball goes to somebody who's on the bench or somebody who's on the opposing team or something like that. Well, we can kind of cheat a little bit because we have our team rebound, which is a possibility across all possible lineups, right? Regardless of who you play, the ball can go out of bounds. And similar to traditional multinomial regression, we can kind of use this as our baseline category and then model the log odds ratio between any individual player getting that rebound and there being a team rebound. So it's functionally the same, like practically the same, but quite a bit different in how you implement it. So we end up with the following equations for the rebounding probabilities. So as we mentioned, the rates depend on not only the player's ability, but everybody on the team, and then that kind of leftover space goes to that team rebound. And you could, in theory, estimate this just by maximizing the likelihood function. It turns out that's really tricky to do in software, so we actually use we use Markov chain Monte Carlo and use the posterior means as our gamma estimates, and we instill the flat prior across the parameter space. So that covers it for things for the gamma level. We can also discuss, before we get to the beta level, I want to just do a quick mug up on adjusted plus minus and regularized adjusted plus minus. So, sorry, I think this is advancing it too, sorry. So this is Rosenbaum's original plus minus framework, and it's very simple in that it assumes that all player contributions can be added up and you end up with the team's plus minus. And the main positive of this the model is that it's box score independent, which is what we're looking for, where you want to credit guys who are helping the team without necessarily grabbing the rebounds themselves. But there are quite a few negatives when we try to apply this to rebounding data, since we're dealing with binary outcomes. So the first is that, right, we're looking at probabilities, and if let's say you have one player grabbing 60% of the rebounds on one team, another player grabbing 50% of the rebounds on another team, you trade them, put them together, they don't start grabbing 110% rebounds, right? That's not how the math works. So we don't necessarily want a linear model in this case. Also, linear model isn't how we think about rebounding, right? Let's say we have some really strong rebounder and we add them to a really strong rebounding team, that's probably gonna make for a negligible difference in that team's rebounding rate. Whereas if we take that same rebounder and add him to a really weak rebounding team, then there's probably a much more pronounced effect on the team's rebounding rate. There's also the issue that the standard errors are very large in the original implementation, and it doesn't actually distinguish between offense and defense. It just estimates the difference between offensive and defensive ability. So one improvement to this model has been Joe Sill's regularized adjusted plus minus, where he has this Gaussian prior instilled across all the parameters, and he basically just squishes everybody to some common mean, which he finds through cross-validation. So that out of the way, we can get into what the beta level model actually looks like. So since we're dealing with binary outcomes, logistic regression is a very natural approach for this. So we treat defensive rebounds as a success, offensive rebounds as a failure, and the probability we propose works like this. So we have the 5 defensive abilities and the 5 offensive abilities denoted by beta D and beta O respectively, and we've set up the signs in such a way that the greater the parameter value, the better the rebounder in question. And if you actually stare at this for a little bit, you'll quickly find some problems with it. but which I'll get to in a couple slides. But assuming we could calculate it, it actually solves a lot of our problems. So we're now in the natural parameter space, so we no longer have this issue of guys making each other look bad because they steal each other's rebounds. Because of the shape of the logistic function, we've captured that whole idea of diminishing returns in the response variable, the team rebounding rate, and we're now handling offense and defense separately, which makes practical sense because they don't rely on the same skill set. But there's two really important issues that keep us from just implementing this directly. We have multicollinearity in the feature matrix, and we have unidentifiability in the likelihood function. So I'll first discuss how we address the multicollinearity. So we could do something similar to Joe Sill, where we have this kind of uniform regularization parameter. The problem is that if we think back to our original example of the 7-foot rim-running big man versus the 5'10" scoring guard, it doesn't make sense to assume everybody's equal, right? So we instead rely on the heuristic that individual rebounding rates are a rough indicator of beta level rebounding ability. So for example, practically what this is saying is that if you have a guy like, let's say, Steven Adams, and another guy like Jonas Valanciunas, we can't use their rebounding rates to determine who's a better beta level rebounder. What we can say, though, is that both those guys are probably much better beta level rebounders than somebody like Trae Young, who's grabbing very few rebounds. So we give this kind of, the idea is to get a rough ordering of the beta level parameters. And the way we capture this heuristic is how we structure our priors. So the idea is that the prior should incorporate individual rebounding rates. But we give the priors enough variance to then go more accurately estimate the beta level parameters. Sorry, no, I'm going too quickly. So that's great. It gives us a rough ordering of what the parameter should be. But the problem is that since we're in a GLM and that we're operating on the log odds scale, it says nothing about what exactly the parameter values should be. And to get an idea of what they should be, we actually need to discuss model unidentifiability. So recall this is the same formula I've put up before. And if you think about it for a little bit, you can just take some constant, let's say C, you can add it to each of the parameters, and they end up all canceling out, and you end up with the same exact prediction, which is not good, right? You have a whole set of parameters which end up with the same exact behavior as far as the data is concerned. But in our specific case, that's not actually a big deal because we're interested in A, ranking all the players, and then B, we're interested in making predictions in new lineups. And if we add the same constant to each of the players, well, that's fine. We haven't changed either of those things. But there's a much more problematic and much more subtle scenario, which I think is best illustrated with a simple example. So assume we have a much simpler league where it's just 1 versus 1 being played, and that we have 2 equal defenders, A and B, and 2 equal attackers, C and D, but that we haven't actually observed every possible lineup combination. We've only observed a subset of them. So the linear predictors are given by the following equations. And the problem is that let's say we add, let's say, 10 to beta dA and add that same 10 to beta OC, well, we end up with an identical linear predictor, but now suddenly we're concluding that beta dA is much better than beta dB, and beta OC is much better than beta OD, right? And it turns out this is actually why regressing everybody towards an identical prior is not a great idea in practice. So we can start playing with all these constants and make any player seem the best. So basically every statistical result is derived under the assumption of identifiability, which is obviously not the case here. So there's no formal way to solve this sort of issue. But one thing we can note is that if we restrict the parameter space, at the very least, we can mitigate how crazy any reordering of the parameters can be, which obviously begs the question, right, like how on earth do you restrict the parameter space in a meaningful way? And to kind of further build intuition for what the problem is, I have the following graph. So let's say we have some true parameterization denoted by beta star. The problem is that we have all these parameterizations that are behaving the exact same way. But for one player, let's say player A, we find the parameterization that belongs to beta star. And for some other player, let's say player B, we're finding the parameterization that belongs to beta 1, right? And we're not making this fair apples to apple comparison. So we're going to actually break the problem down a bit further. We're going to rephrase this issue as two questions. One, how wide do these clouds need to be? Because recall, we want to make them as narrow as possible. And secondly, how far apart do the clouds need to be for us to be able to express the relevant probabilities? So to answer question one, I propose a thought experiment. Assume we could take the strongest and the weakest rebounder in the league and clone them, and that we play the strong I'm going to use defensive rebounders in this case, but you could do the same on offense. So you clone the strong rebounder 5 times, the weak one 5 times, and you play them together against some average offensive rebounding lineup. So we obviously don't know what these probabilities should be, right? That's the whole question we're trying to answer. But what we can say is that just heuristically, that the strong lineup probably isn't grabbing more than 90% of the rebounds, and the weak lineup isn't grabbing more than is grabbing at least, 50% of them. And if you look at the empirical data, this actually seems like a very cautious estimate. And we want to know how narrow can we make the difference between the strong one and the weak one. So you can reformulate this as an optimization problem, which again, we're trying to minimize the cloud side with allowing enough variability to express the probabilities. And we can solve this really easy using Lagrangian. And we can plug this all in, and we can just find that the size of the cloud, based on the thought experiment, needs to be at least 0.34. And this is astonishingly close to the spread you actually see in individual rebounding rates. And we could do the exact same thing on offense, with allowing for a slightly smaller cloud, and can find that the size of the offensive cloud needs to be 0.292, again, based on a similar thought experiment, which answers at least roughly right question one. We have this rough sizing of what the cloud should be, which is good. We have some bound on how crazy the reordering can be. So for question two, I know this might be for question two, how far apart the clouds need to be, there's a trick. You can notice that, let's say you take the true parameterization, you can express it in terms of any equivalent parameterization along with some shift in these clouds, right? So practically what this is saying is that you can pin down those two clusters wherever you want, as long as you add in some free parameter to be able to space them out accordingly and capture those probabilities. And the key idea is that we can actually learn what this shift should be by looking at the empirical data. So far I've been using words like restricted, unrestricted, very informally just to help build intuition. But the idea is that by using a Bayesian model, by restricted, we mean informative prior distribution, and by unrestricted, we mean uninformative prior distribution. So we propose the following Bayesian model for the beta level rebounding. So we have the parameters centered at the relevant rebounding rates with some variance sigma squared, which are the restricted parameters, right? And then the unrestricted intercept just has the unrestricted shift has an improper uniform prior over the real line. And YLK denotes the kth missed shot in lineup L. And so I've defined everything here except for those variances. So we chose sigma squared to be equal to 4 times the empirical variance of the variance of empirical defensive rebounding rates. So this, because of all the unidentifiability issues, is by no means like a formal solution to the problem. It's very wishy-washy, hand-wavy, like heuristically based. So we thought it was really important to run a simulation study to make sure the methodology is reasonable. Again, this would, if I went into all the details of what was done, it would double the length of this presentation, but the key points are that the sample sizes are comparable. We recovered the original parameters by distributing that shift equally amongst all the players. And then we did 2 versions of the simulation, one where there's a high variance in the true parameter values, and then one where there's low variance in the true parameter values to get an idea of how robust the methodology is. And all in all, we were quite happy with how with the method's performance. So we moved on to real data. So before getting into predictions, we'll discuss the estimates to make sure they make sense. So on the x-axis here, so we'll start with the beta level, excuse me. So at the x-axis, we have the posterior means. One last note is that all the beta parameters were estimated using Markov chain Monte Carlo. So on the x-axis, we have the posterior means. On the y-axis, the posterior standard deviations. So we have this normal-ish this curve in the posterior means, which makes sense of how we think about ability being distributed amongst the players. Another key thing to note is that for all players, the prior variance is much greater than the posterior variance, which is reassuring, right? Our choice of prior was compatible with the data we ended up getting. One key thing to check, though, is to make sure that since we have the rebounding rate in the prior, we're not just spitting that back out, right? That we're actually learning something new using our data. And by construction, obviously, there's correlation between the prior mean, which is on the x-axis, and the posterior mean, which is on the y-axis, but they're not exactly good, which is equal, right? We've learned something new about what's happening at that beta level. We can do a similar thing for the gamma level estimates, where again, on the x-axis, we have the posterior mean, the y-axis, the posterior standard deviation, and we again have that normal-ish curve appearing. But one key thing to note now is that since we're conditioning on which team has collected the rebound, we end up with a lot fewer observations on offense versus on defense. So there's a lot less variance for the defensive estimates than there are for the offensive ones. So a lot of our estimation results make practical sense, which is why we can justify making predictions in new data. So we use data from the 2020-21 NBA season to estimate the parameters. We use data from the 21-22 season to make model predictions to see if the models learn something meaningful. One obvious problem with that is that we end up with a whole bunch of new players in the data set, right? So we just decided to ignore observations of a new player, whether that be because they just signed their first contract, were drafted into the league, something like that, which means we ended up with about 25,000 missed shots of like the 100,000 that took place during the year. But within these 25,000 samples, we made two distinctions. So we had what we called scene lineups, which are lineups where the 5-man defensive combination appeared in the training set, and unseen lineups where at least one player on the defensive end was new. And the idea is that if the fit here for the scene lineups is much better than the fit for the unseen lineups, then we're probably overfitting to the training set. And thankfully, that didn't seem to be the case, especially when you account for the difference in bin sizes. So this plot is about predictions. This is about predictions at the team level, but we can also make predictions at the individual level by first predicting which team will get the rebound using the beta model, and then predicting which individual player gets it using the gamma model. And again, we were quite happy with the fit, but as we'd expect, the offensive fit is a little bit worse than the defensive fit, again, probably due to that increased variance in the offensive gamma estimates. So to get back to our original question, which guys are helping the team, versus which guys are just kind of snagging rebounds for themselves, well, I've included this plot to help illuminate the situation. So on the x-axis is the posterior means of the betas, and on the y-axis is the posterior means of the gammas. And the idea is that players down here are collecting disproportionately little rebounds for themselves relative to their team impact, versus players in the top left are collecting disproportionately many rebounds relative to their team impact. And the idea is that I've included a couple telling names here to help illustrate to capture some conventions of heuristics about stat patterns versus team players. And if you look at my thesis, I actually have the full table for all the players and not just this subset. And when you look at that full table, there's actually quite a few interesting trends that appear. So on offense, on the offensive glass, these offensive engines who handle the ball a lot tend to be underrated, which might have to do with the fact that they're breaking down defenses, they're forcing rotations, which helps their teammates get into better rebounding position by sliding through the cracks, but they're not necessarily grabbing them for themselves. Similarly, long-range threats tend to be underrated offensive rebounders. This might again have to do with forcing really long closeouts, drawing opponents away from the basket, and therefore helping their teammates grab rebounds. And on the opposite end, ball handlers tend to be overrated defensive rebounders. This might be because since they're guards, they're not in charge of boxing out any big men, or maybe teams want to really efficiently begin their fast break and are funneling the ball to their guards artificially, regardless of their involvement in the rebounding scheme. Also, on offense, traditional centers tend to be overrated. This, again, might have to do with the fact that just by virtue of playing center, you're asked to stand near the basket, and a whole bunch of rebounds just fall into your hands, regardless of if you're good or not, and actually helping the team. So that was most of the methodology, at least what I include in my thesis. But there's a few limitations that you need to consider, at least when you're applying this to the field, in the field. So the first is that how you handle block shots is really important. The way we've defined the model, if you're blocking a lot of shots on defense, you're technically hurting your team's rebounding ability. And if you're getting blocked a lot on offense, you're actually helping them. You're helping your team's offensive rebounding ability, because most block shots are sent out of bounds. This is something that we didn't bother dealing with because it doesn't tweak the methodology, but in practice, when you wanted to conclude who's better, is really important. And there's obviously things we've omitted for the sake of tractability, like days rest, home court advantage, stuff like that. And this was running on my poor little desktop, who was taking 3 days to estimate all the parameters. So it might be something, like if you had more compute, it's something you could easily include using this methodology. So this is the stuff I've referenced. My thesis can eventually be found here, but since it hasn't been put up yet, check back in a couple months. I don't know when that happens. But yeah, that was basically it. Thank you for listening.
Are there any questions for Nicholas? This one over here.
Hey, Nicholas, thanks for the talk. I apologize. I may have not made the connection, but suppose you're a player who boxes out a lot, and that you're very effective in that way, but you don't actually collect the rebounds. Is it through the prior something like that would be accounted for?
So no, so you get your posterior estimate for the beta, right? The problem is that if you squish, so how you estimate that posterior is not obvious, right? If you use the same prior for everybody, we run into that issue of there's no identifiability. You might be getting the wrong answer. You might be getting the answer from system 1 for one player, from system 2 for another player. So how do you keep that from happening is how we do it in the prior layer. We count for rebounding rate in the prior and then look at the data and then update that belief based on the team rebounding. So another way to kind of think of this practically is that unless there's evidence to the contrary, if you're grabbing a lot of rebounds yourself, we're assuming you're a good beta level rebounder. But we can then go update that belief based on the data. Does that answer your question? Or?
So there's some individual aspect of rebounding rate that kind of tunes.
So that's how we set it up initially. The individual, like if you're grabbing rebounds, it tweaks what your prior is. And then depending on what happens when you're on the court, we can go update that belief. So like, for example, I think if I should have maybe spent more time on this slide. Before the start of the season, we're assuming Robin Lopez is not that good on the beta level because his priors, we haven't updated yet. But towards the end of the season, his posterior jumps out way further than, so this is, jumps out way further than what his prior is. Like in this case, the gamma is very close to the prior. Is that clearer?
Yeah, it gets me closer. Yeah, thank you.